So today's lesson is a short bit about thermal energy and some of the concepts that are going to be important when you're looking at building your exoplanet habitat or your solution to your design problem. So this is going to use a lot of the same language that we were using earlier in the year in thinking about conservation of energy and about energy being transferred from one form into another. Now, back in the fall, we tended to ignore problems like this. A block is being pushed a distance of 2 meters to the right along a table with a force of 8 newtons, but it's moving at a constant speed. There's two forces acting on this block that are doing work. It's also a nice recap of the fall. I have some sort of pushing force pushing it to the right. And I have a force of friction acting on it to the left. I'm going to call that FR for friction. So I have two forces doing work. Of course, I still have gravity acting on it, and I still have the force from the table holding it up. But in terms of the forces that are doing work, I care about these two. This block is also moving 2 meters to the right. So if I think about the work done by the pushing force, work was equal to force times displacement in the direction of the force. My force here is 8.0 newtons. My displacement in the direction of the force is 2 meters for a work done of 16 joules. Now we talked in the fall about how work needs to go into changing either the types of energy present or the amounts of them. And we did a lot of examples where work gave an object kinetic energy. But we were ignoring the fact that this doesn't happen in isolation. My frictional force here is also doing work on this block. It's a force of 8 newtons, and the displacement in the direction of the force is minus 2 meters. The direction of the force is to the left. The displacement is to the right. So in the left direction, it moves minus 2 meters. And what this represents is heat loss to friction. If you imagine rubbing your hands together, that frictional force of one hand over the other warms up your hands. It creates thermal energy. And that's the piece that we're going to need to consider in this project, is how thermal energy will be affecting our system. In the case of this block, all the work done, the 16 joules of work, is lost to friction and becomes heat. And when you're building your habitats or your solution, you're going to need to consider how thermal energy is going to be affected by where you find yourself. So we'll start with a familiar concept about thermal energy, and that's temperature. It's somewhat problematic because the typical definition of temperature that someone will give is to say how hot or cold something is. This link down at the bottom here is a great Veritasium video that I'll link to on our Canvas page called The Misconceptions with Temperature, and how this definition is very problematic. What we need from a scientific perspective is one that's based on a physical property and not a sensation. So some of this might be familiar from grade 8, but how we define temperature in a scientific sense is the average kinetic energy of the particles in the substance. So back in grade 8, you looked at the main points of the kinetic molecular theory, being that all matter is made of small particles, there's empty space between them, they're constantly moving, and if we move that into energy terms, they have kinetic energy. The particles are colliding with each other, with the walls of their container, and that energy makes the particles move. The more energy the particles have, the faster they move. There's my kinetic energy. And then this is the piece that we're going to interpret in terms of potential energy, the farther apart they get. So when you have something that's a solid, the molecules have very, very tight bonds between them. They're tightly packed together, they cannot move freely, and they can only vibrate. So if I imagine a beaker with some sort of block in it, maybe this is just a block, it has all of these little molecules packed very, very, very tightly in. And how I imagine that is trying to walk down the hallway when it's full of kids and you're linked elbows with the person next to you. You're holding on very, very tightly to them. You're not free to move. They're not free to move. And there's a very strong bond between you and the other person. So solids have a very low kinetic energy, but a very high potential energy. You can also think of that like a rubber band and how tightly they're held together. In a liquid, this is the mid-range on both, where the molecules are farther apart. They're not as tightly held. This would be like if you're walking down the hallway having a conversation. So there's something bonding you together, but it's not something that is so forcefully attaching you to each other. And they're moving a little bit. They have more kinetic energy than the solids. They have less potential energy than the solids. And if we move all the way to gas, those molecules are so far apart, they're moving around so quickly, and ideally, they have almost no potential energy. But they have a very high kinetic energy. So when we're heating a liquid, for example, and taking water, say from room temperature up to boiling, that thermal energy is becoming kinetic energy. When we're boiling the water, moving from a liquid to a gas, it's not gaining any more kinetic energy, but that thermal energy supplied by the kettle or the stove is going to break those bonds or to loosen them. So there's a few different scales we use to measure temperature. We've probably heard of most of them at this point. Celsius is the one with which we're most familiar because that's what we use in the metric system and for our weather. This is based on the physical properties of water, where 0 degrees Celsius is the freezing point and 100 degrees Celsius is the boiling point. The Kelvin scale is the one that's more directly tied to this conversation about energy. This is based on a theoretical minimum where that kinetic energy of the particles can be 0 joules. Or if I think about it in terms of motion, where they're completely at rest. This is a theoretical minimum. We haven't found anywhere naturally that is closer to that than the background radiation of the universe at about 2.7 degrees Kelvin. There are labs on Earth which have gotten down to fractions of a degree Kelvin and looked at how matter behaves under those kinds of conditions. So to convert between the two, Kelvin minus 273 will give me the measurement in degrees Celsius. So 1 degree is the same, the size of 1 degree is the same, it's just that the whole scale is slid over. Only a couple of countries, the US and maybe 1 or 2 more, use the Fahrenheit scale. This was created based on 3 temperature points: normal human body temperature, the temperature at which water freezes, and then the temperature at which a particular salt water mixture with ammonium chloride freezes. So Fahrenheit's not a terribly practical scale. It's not based on one substance like Celsius, and it's not based on energy terms like Kelvin. Honestly, the only time I use this is when I'm on vacation in countries that use it for their weather. So how I convert is the Celsius temperature is equal to 5/9 times the Fahrenheit temperature minus 32. So unlike Celsius and Kelvin, 1 degree Fahrenheit is a different size than 1 degree in the other 2 scales. That 5/9 means it's not just a straight slid sideways conversion, but that there's a little more arithmetic involved. So the section or the topic that's going to be important for your project is this idea of heat and thermal energy transfer. So heat is just a form of energy. The term I just used of thermal energy is a synonym for all intents and purposes. But this is very different than temperatures, and this is one of those misconceptions that people often have. So what I have here is a material that has a section at 0 degrees Celsius and a section at 100 degrees Celsius. And what's happened over time is that thermal energy has transferred from the hot section to the cold section until their temperatures have equalized. So this is what we call thermal equilibrium down here. It's just a fancy way of saying equal temperatures. So what we have happen here is that we have this form of energy that's being transferred from one object to another because of those temperature differences. This happens until they reach thermal equilibrium. At which point there won't be any net energy transfer between the two sides. So because this is a form of energy, it is measured in joules. In terms of a symbol, if we were going to be doing calculations or if we were labeling this quantity somewhere, it is still a capital E for energy and then a subscript of an H. Some older books you see use a capital Q, but I prefer this because it emphasizes the fact that this still is energy. So what you'll have to consider when designing your habitat for the exoplanet project is how you're going to mitigate heat loss. If you're on a planet that doesn't have much of an atmosphere, you don't have that blanket to keep you warm, or to keep the planet warm rather. Or maybe you're on a planet with a very, very thick atmosphere like Venus, where you need to try and keep cool. So it's important to consider the three ways that this thermal energy transfer happens. So the first one is conduction, which is in solids. You have these molecules colliding with each other, and when they collide, they transfer energy from one molecule to the next molecule to the next molecule. So this is because of objects in contact with each other. And it will transfer that information, almost like dominoes falling over. It will transfer that energy back from the heat source, from the hot to the cold, and into your hand. Convection happens in fluids, and a fluid is defined as a liquid or a gas, basically anything that's not a solid. That happens because of these density differences. So if I have a source of heat at the bottom here, it's going to take some water. It's going to make it expand. Things expand when they heat up, and when that expansion happens, it makes that bit of water less dense. So it rises, it follows the red arrow up to the top. Some of its energy is then lost to the surroundings or maybe lost to the pod itself. And when it cools, it condenses, it becomes more dense, and it sinks back down again to get heated up. We see this happening in our atmosphere with clouds in the water cycle. We also see this happening in the mantle of our Earth, and this is what drives continental drift. The final method is radiation, and this does not have to have anything in contact with each other. Conduction had physical objects in contact. Convection had that bulk movement within a fluid, so it's not really objects in contact, but it is one singular object circulating. Radiation can happen through a vacuum, which is what makes it different. So it's an electromagnetic wave, usually in the infrared spectrum. If you remember back to the electromagnetic spectrum picture we looked at a few lessons ago. So electromagnetic waves can travel through a vacuum and reach from the sun to the Earth, or in your case, from your exoplanet star to your planet, or from fire to hands. So when you think about your habitat, you think about protecting your settlers, you're going to have to think about how all three of these apply and how you might mitigate either for heat loss or for heat gain to make sure that your habitat is comfortable and appropriate for the context in which you find it. This is very much going to depend on your exoplanet and what its climate is like.